तो लालाबंती हो गई उससे बिल्कुल ही, बिकेम फैट, क्योंकि बहुत डिप्रेसिव होता है। इसकी एडमिशन होगी वहाँ पे, और ये देखो जी, ये इतना, इसका क्या हुआ, तो बाहर निकलते लोग ताने मारते हैं ना, तो पेरेंट्स की भी एक्सपेक्टेशन होती है, वो भी फ्रस्ट्रेट हो जाते हैं, हमने इतने पैसे लगाए, ये करा वगैरह। एनीवे, that's the way the nature of the beast is. All right, let's move forward on this. Got it? I will now start working on this. All right. So we are. So I think yesterday we were discussing some questions, and we also discussed contact forces and stuff like that. आज जो है, I want to explain you few more things. But inclined plane का जो concept है, ये बहुत जगह पे होता है। ये रैंप होती है, by the way. Okay, I hope you know that it's a ramp.
Yes, sir.
You're talking about a ramp. The difference in the anything on the horizontal and a vertical coordinate axis, y and x, and this is nothing. There is no difference. Only thing is the choice of axis. Now our x-axis has shifted by an angle theta and looks like this. Okay, so this is your x dash, and therefore y also has rotated by an amount. Okay, so which is y dash. So any block of mass that you keep now, okay, now thinks this is the x-axis being referred to, and anything perpendicular to the new x-axis is your, so I can call it dash because it's a new coordinate system, and I can call it a y dash, and on this side I can call it minus y dash, and on this side I can call it minus x dash, right? So essentially what we're talking about is the fact that inclined plane is a ramp on which you keep a mass like you do on a horizontal surface. If on a horizontal surface you feel gravity pulling you down, and then you are getting this, so you're applying a force on earth, which is this. Earth is applying a force on you, which is normal reaction. This is pretty straightforward because it is x and y axis. But in the situation of an inclined plane where the coordinate axis has changed, there will be a small change in the way we solved such a question. Although the weight direction will never change, जो supposedly weight है या अर्थ के ऊपर ही जो प्रेस कर रहा है, अब अर्थ थोड़ी सी इंक्लाइन लेवल पे आ गई, राइट? सो दिस इज योर force you're experiencing from the earth, but your surface is not inclined, so your normal reaction has to be perpendicular to the surface. So this is your normal reaction, n, and the weight now will be along the new coordinate system. It is like saying पहले मेरा coordinate system ये था, this is my coordinate system, my force is this. I'm going to resolve my force in two parts. One is f cos theta, the other is f sin theta. This is your old system, the old way of working, right? But let's talk about this particular system in which your x-axis and y-axis have now rotated by a certain degree. If this is your weight and you have to resolve the weight like you did here, just give me 1 second here. So now resolution will happen in the new coordinate axis. The old coordinate axis is no longer important to you. What is important to you is your new coordinate system. That's the only difference. And in the new coordinate system, you will do resolution of the quantities which were earlier in y-axis and were looking very easy. But now they are, you know, if you look at this, there is no resolution required. But if you look at this, if something is making an angle in the xy plane, like this force, you can break it down into two parts. Similarly, if you look into the new x and y axis, which is this and this, right? There is a force which is making an angle in the new x dash y dash plane, which is a bit inclined. It looks like this. And the force looks like this. So this is your y and this is your x dash and minus x dash. So this is a weight. The way you will divide this weight along the incline is this component. This is mg sine theta and this is your mg cos theta. So you have used something very similar to what you were doing here. The only difference is because your what used to be a vertical force appears to be a force at an angle to the new coordinate system. So if this is theta, this is 90 degrees, this is 90 minus theta, and therefore this is also theta. And if you break it down into two parts, the way I've done this, the normal reaction, this is one component, which is the mg cos theta part. I'll just redraw this in a cleaner manner so that you can realize it. So this is your mg cos theta and this is your mg sin theta. So same. The only difference is now because the coordinate system is different, the vertical no longer remains vertical, but has to be resolved in two parts. Make sense? Any questions in your mind that I don't understand this? I can redraw this figure for you so that it looks a lot cleaner.
redraw कर दीजिए.
So that it looks a lot cleaner to you. It didn't come across as a very clean figure. So this is your mass. Now the new coordinate system is inclined at an angle theta with the old coordinate system. This is old, this is new. And there is a weight which is downward. Okay, so this is mg. And this is your mg sine theta. And this is your component which is mg cos theta. And you get back, because you are pressing the ramp with mg cos theta, what you as a block will feel is a normal reaction on you. So which means the only force in this diagram. So if we divide the forces in y and x the way we do resolution, we are saying in y-axis mg cos theta is equal to n. They're balanced. The block is not flying off the ramp. And in the x-axis, the only force you have is mg sine theta. So here there is equilibrium in y-axis, but in the x-axis, mg theta is equal to m into ax, because this is your new coordinate system. So the acceleration with which you will go down this ramp will be a x dash meaning the new coordinate system is equal to g sine theta. You have to know this basic thing, and this will further develop into Newton's second law, etc., etc. But you should know on a ramp, it is the change in the coordinate system and the way you start looking at the same weight vertically downwards now has two components. हाँ जी.
अगर कोई external force apply हो रही हो block पे.
Exactly. So I hope if you have a block placed on the ramp, the block will go down with an acceleration of g sine theta. I hope this is clear in your mind. It will go down with an acceleration of g sine theta. Is that clear in your mind?
Yes.
This one, right? G sine theta as a concept. And then there is an equilibrium also in the vertical. So I'm assuming you understand this now. Let's move to the second situation. Now somebody says, all right, let's take a real life example, because ramp, you will see a lot of questions pertaining to ramp, okay, which are very important. So this is 5 kgs, and therefore what you see is 5 into 9.8 is equal to 49 newtons. This, for example, is 30 degrees. So this is 49 sine 30, and this is, of course, 49 cos 30, and there is a normal reaction which it gets back n. So if I were to write equations of all of this, I will say the normal reaction acting on the body in the y-axis in the new coordinate system is 49 multiplied by cos of 30 is equal to 49 multiplied by cos 30, which is root 3 by 2 newtons. Okay, so that's your normal reaction. And I will say the body is going along the x-axis downward because I can see the arrow is in this direction. And I will say the acceleration of the body in the x-axis, the new x-axis is g sine theta is equal to 9.8 into 1 by 2 is equal to 4.9 Newton. So we have done a real life example of this situation. Now, how does it look when we start using this in Newton's second law, which means this was purely the weight of the body which is pulling it down. Now, if I bring in a change in this and say there are external forces involved, the easiest could be what push force do I apply here so that this does not move? Answer that. What push force I apply on the block so that it does not move? What do you think? It doesn't go down the ramp.
F1 वाली ना?
Yes.
Sir, वही same,
Equal and
negative.
opposite, right? Equal and opposite.
Yes, sir.
Equal
Negative
and opposite.
49.
Correct. So I know
Negative
the exactly. So I will write it as 5. So 49 sine 30, right? Identical.
Yes.
Whatever is this, opposite to that. So the
Like
magnitude
negative, like negative लिखते हैं क्या आगे?
you can to show the
Sign
the
convention.
direction. That's correct. So 49 into 1 by 2 is equal to 24.5 newtons, right? This is the force you will apply to prevent the block from coming down. Now, in the second situation, a person comes and says, I will not push it with a force of 24.5 newtons. I will not. I will push it with a force of 49 newtons upwards, which means now he has told you his F push is 49 Newton, and he is also told it is along the ramp but in the upward direction, which means the body is gaining the energy, potential energy. The height of the body will go up. Okay. Now, the net force, let's draw the free body diagram. The net force is this. In the normal reaction axis, everything is still whatever it was. This is normal reaction. This was 49 cos 30. Everything is balanced, and you are getting pulled because of your own weight by 49 sine 30, and you are now facing an external force of 49 newtons. And if you calculate this, this was 24.5 newtons. If you notice, in the y-axis, everything is balanced, nothing to worry about, right? So there is nothing to worry here. Therefore, the net force external is going to be upward, is going to be 49 minus 24.5 is equal to 24.5 newtons. Any questions in your mind pertaining to what we did? We applied an upward force to take the block away from Earth towards a higher point, which is this direction. And we had to overcome this force first, which we did. We subtracted this force, and the balance force is now being used to take it towards the higher point on the ramp. Any questions in your mind that come? For this particular situation, we can create any number of situations, which we will, but you must have mastery over the basics of inclined plane first. We will do the complex
Sir,
part.
अगर ये force like downward की तरफ लग रही हो?
All right, so let's say, all right, good question and very relevant question actually. So not only the g sine theta, I'm not drawing the y component again because I'm assuming it's in equilibrium right now. So this is mg sine theta. And now you'd say I'm going to push it down or pull it down. it is my choice. I can push it from this side, or I can attach a string and pull it down and apply half of this force. So this is mg sine theta by 2. If this was 24.5 newtons at 30 degrees with 5 kgs, then this is 12.25 newtons. So the net force which you get now downward is 24.5 is 12.25, right? So add these two, what you get is 36.75 Newton. So they're in the same direction. They're actually two vectors in the same direction getting added linearly. OA plus AB is equal to OB. Tail, head, tail, head. Vectorially, this is what we're doing. I hope you understood this part of it.
Yes.
All right. Excellent. It's very important to have mastery on the inclined plane, because this will get complex and more complex as we do advanced level questions. But for the timing, this is what you're supposed to know. Now, let me ask you a question by giving you a quiz and see whether you can handle it, okay, with the knowledge you have acquired so far. So let's say this is your block. This is your mg. This is the mg sine theta. This is mg cos theta. Now you are pushing it with a force of, and this is 5 kg. Now you're and this is again, say, for the ease of it, 60 degrees now. This is 5 kg. You push it upward with a force which is 10 newtons, but there is an external force between the two surfaces apart from the action and reaction pair. They always are going to be there. We have to ignore it because this particular object is not flying off the ramp, right? So we are only concentrating on forces along the ramp. That's it. Now the force of friction is there, and say it's a very typical scenario. The rough surfaces of the block. So block has roughness below it, okay, and there is a roughness here, and the ramp also has a roughness to it, right? So when two rough surfaces meet each other, there is a resistance to motion. If you keep this block on top of this particular ramp and try to push it, the roughness below the block and the roughness of the block will prevent the motion of the block, which means if I try to push it down the block, the friction will go up. If I try to
But
pull
sir,
push
अभी friction पढ़ ही नहीं रहे ना.
पढ़ ही नहीं रहे. Don't worry about it. We are not. We're still not studying. I'm just explaining you so that you can solve this question. Friction always opposes the external force. Okay. We're not still concentrating on knowledge of friction. I'm just telling you, there is a force which is, in a way, whatever is the direction in which you push the body, it reverses and starts acting on the body and is in picture because of the roughness. You want to call it friction. If you don't understand it, friction, call it a frictional force, which always exists. Now I'm telling you, this force is a fixed force, which will always be there, just reverses the direction based on the external scenarios and the tendency it exhibits under the influence of external forces. Now this force, which is your notional or a frictional force, is now say 5 Newton. You have to take G is equal to 10 meter per second square. Now I want to push this body upwards, right? I have an external force of 10 Newton, and I know there is a force of friction or some force which always remains fixed, but has a tendency where whichever direction the block will try to go, the friction will oppose it always, right? It is always in reverse of the tendency of the block. My question to you is, if I'm pushing it upwards with my hand, what happens, and what is the net force being experienced by the block? And this 5 newtons is coming from the surface, because surface and the block are in touch with each other. So if you push the block upwards, the frictional force comes in the reverse direction. Think about it very carefully. You can calculate mg sin theta very easily, right? So 5.
Gravity हम 10 ले ले क्या? Acceleration due to gravity.
Absolutely, you can. No worries.
Sir, मैं एक बार खुद try करना चाहता हूँ.
Okay. I'm just okay. No worries. Do it yourself. That's the best way to solve it. And remember, this force appears because of the tendency. It appears. It is not there. It appears because of the tendency to go up and down. Okay. Okay.
ये आना चाहिए.
All right. Okay. So understood. So let me discuss this, the way of thinking. Okay, and let me challenge it. Not a bad attempt. It is a good attempt to start with. Okay. So there is your block. This is your block. The block actually, if it has nothing, would like to come down with an acceleration of g sine theta. Therefore, it comes down like this, facing this force. Right. So let's calculate this force in this example. You calculate it as 25 root 3 newtons, right?
Yes.
All right. And there is so this force, it does not appear, it is still there, right? It is there just by virtue of the mass. The mass experiences this force. It is there because of gravity, obviously. And then there is an external force, which is 10 newtons. Tell me, what is the resultant of these two finally?
10 minus 25 root 3 minus 10.
Agreed. So tell me if these are the two influences which exist on the mass, which direction it wants to go. If I say this is the downwards, and therefore if the tendency is to go downward, in what direction will the friction appear?
Okay, opposite, upwards.
And therefore 25 root 3 minus 10 brings in that feeling of downward, and therefore the friction appears and says, okay, then I will be also upwards, and therefore more subtraction from the. So therefore throughout the motion the body faces this much amount of force.
Okay.
So of course you don't understand friction fully well, but I hope this key word, the tendency, will stay in your mind for a long time.
Sir.
It will, because you thought this is there. It is not. It appears. I told you. It appears.
Okay.
It decides the tendency first. Okay, let's forget the friction part. We will discuss in depth one more problem.
ये चीज नहीं पता थी.
कोई बात
ऐसा.
नहीं. No worries. You are just a beginner, and you're doing good. Nothing to worry. All right. So let's say that this is one more situation. And now you have a block of mass, but this time we are going to use the connected string aspects of it. And it goes down like this. And this is of 10 kgs. This is of 5 kilograms. This is 60 degree. There is no friction, nothing. It's a normal case. It's a smooth surface. Okay, you don't have to worry about anything. It's a smooth surface. With the help of the data which is given to you, you have to find the acceleration of the system made up of the two blocks. They're connected with a common string. Acceleration of the system. And the second thing you need to find is the tension in the string which connects the two masses. Now your knowledge of how does a tension play out in the string, the knowledge of a ramp, the knowledge of the inclined plane, all of them have been clubbed together in one question. Give it a
So
shot
let's
now.
say,
Give it a shot and resolve the forces now. Pick up free body diagram of 10 kgs separately and the free body diagram of 5 kgs separately. And then say, okay, I'm writing, I know I have to find two unknown variables. I'm going to apply a Newton's second law on this, and I'm going to apply a Newton's second law on this. But for that, I need to isolate them first and show them separately on a diagram. So you draw your first mass here. I'll just draw the incline and leave the rest to your work. So just focus on the mass on the inclined plane and start marking the forces that are getting applied. Once you get proficient in a free body diagram, things will ease out for you. And of course, this is 60 degree. Now your only job now is to first draw the free body diagram, show the forces acting, and then write the second equation of motion. All right. So this is your mg. Okay. Okay. Just a small correction. And that is why it's important that you write it, right? That just a small correction there, and good that you wrote it. Since the inclined plane is a new coordinate system, it doesn't mean the weight will become perpendicular. The weight due to the Earth's pull still remains what it was. You have mathematically only put it on a new, what should I say, on a new playground. Your playground earlier was an x and y axis, but now it has become this. That does not mean the weight will not be what it was. The weight direction will remain it is. Okay. Okay. So you want to show the normal reaction, right? Well, okay. Let's draw your normal reaction. Okay. It's because it takes time to write. I will just draw your normal reaction, just opposite to mg cos theta. Fair enough. Fair enough. We will go with that.
supplied by the pulley.
Yes, it is also connected to the pulley. And you know how the tension works at the end. The tension in the string, when it touches the mass at this point, what does it do? It pulls, absolutely. So there is an upward force coming from the tension. You can call it F pulley. I will call it tension actually. Tension in the string. Okay. F pulley gives a different impression, but yes, to start with, it's okay, but try and use T because it's in that string. The string is pulling it. The tight string is called as a taut, T-A-U-T, tight string. All right, so now write the second equation of motion for this particular free body diagram. Your free body diagram looks good now. Now write the second equation of motion for this. Which means you will write Newton's second law that stated that the net external force, howsoever number of forces you may apply, vectorally will be equal to m into a. If you're writing some x's, then this will be in the same axis. So you're writing everything along the ramp. So therefore, write the equation along the ramp. And you can assume the direction yourself. You don't know whether this is going up or down. Assume it is going in a particular direction. Say upwards.
सर हम इसको like tension minus mg sin 60 लिख सकते हैं.
Correct. बिल्कुल लिख सकते हैं. You're right. And that's the point I'm trying to drive home. You're assuming, therefore, that the tension in the string, right, is taking the body upwards. Let's assume that, okay? I'm good with that. Doesn't matter. Right?
But ये heavy weight है.
It doesn't matter. You don't know how the tension will play out. You have no clue. It's your best guess what you've done. It is fine. Don't get carried away by the weight. The angle also matters sometimes. The angle can vary a lot of things, right? So you don't know what at this angle may make mg sin 60 feeble in front of the other mass. God knows. But so go ahead with your gut feel and solve it. And so this is the external force on this, and this will be equal to what? As per Newton's second law?
ma max.
Right. So let's just write ma because we know it's x only. Okay. So you have a two variable equation, tension and acceleration, clearly visible to you. Right. Now look at the second mass. Go to the second mass and draw the free body diagram for that. They're connected systems. So both are moving with the same acceleration. It's a single string.
ये तो vertical में है ना.
Vertical में. इसमें तो वो you don't have that problem at all.
Tension ऊपर की तरफ से लग रही है.
Right. Always pulls. Always pulls. Yes.
और this would be mg.
That is correct. And the system is moving with an acceleration, right? The system is moving with an acceleration.
So the net force would be T minus mg.
Okay, so which means you're making this also move in the same direction or opposite direction.
No.
You can decide one direction at a time.
Oh.
You have decided to take the string upwards, so this mass should go downward. The whole system is moving in a same direction, not opposite. Right. ठीक है? mg minus t. Correct.
This is true.
Yes. Equal to m into a. Yes, m into a. The magnitude of acceleration is same because they're connected bodies. They're moving in the same acceleration. Fair enough. So now you have two equations, but remember, you should have taken this to be not m, but a different m. The masses are different. So you could have either written m1 here, and in the second equation, you could have used m2, so that the subscript is clear to the reader.
mg.
Correct? That is correct. Absolutely right.
तो add कर देते equations को.
Correct. So t will go.
T will go.
Yes, that is correct. बहुत बढ़िया.
m2g minus m1 g sin 60 equals to 2ma.
Correct. Is it 2ma or the masses are different? M1 plus M2A. Correct. Let's be very careful on the subscripts because you're new. Once you get proficient, it's fine. Okay. Now put the values. Put the values now. So M2 was 5 kgs.
T minus G10.
Right. That is correct.
25 to 3
Right.
into
15.
8, 15A.
That is correct. Right.
मैं इसमें से 25 कॉमन ले लेता हूँ. 25 minus root 3.
2 minus. You took 25 common, so 2 minus root 3. Correct.
2 minus root 3.
Mm.
115.
Mm.
5 upon 3.
Fair enough. So root 3 is 1.73.
पूरा like इसको irrational form में नहीं
No, you have to solve it. This is not maths. You can solve this, right? 2 minus 1.73 will be 0.27.
1.7
ठीक है 1.7 ले लो 0.3 आ जाएगा
5 by 3
yeah
into 1.3
into 0.3
sorry 0.3
so 15 by 30 right 3 कट गया
0.5 नहीं
3 by 30 yes 0.5 ठीक है 3 by 30 was 0.5 meter per second square which means your assumption was right it is actually going upwards it is find the tension now by putting back in one of the equations you can find the tension also
सर वो निकालूं अभी अब
have you understood what you have done
yes
more
sir
importantly I'm not worried about your calculation right I'm just worried about where you stand on understanding the ramp clear hai?
clear है sir
Not very hard right matlab just apply yourself a bit you can all right let's talk about more importantly we have obviously done some questions on Newton's second law we have seen some glimpse of friction though we have not studied friction let's understand the law of conservation of momentum okay law okay, let me shift to the second page now because I think it's key I'm shifting to the page number 2 okay you're there right
yes.
all right so I'm here okay let's talk about law of conservation of linear momentum. What is your understanding so far? This is very closely associated with Newton's second law, a special case actually, law of conservation of linear momentum. Any understanding you have developed so far, feel free to. So momentum, the amount of motion which is contained in a body. And we're saying the motion is remaining conserved.
Yes.
So you're not able to decrease the motion or increase the motion, which means there is no external force on the system. This numerical is very close to the one which we did for the machine gun, where the bullets were coming out and there was some momentum getting generated, but an equal and opposite momentum was getting generated in the opposite direction because there was no
basically
external force.
Second law of motion use कर रहे थे.
Yes.
Force use कर रहे.
Yeah, we actually, and this is the way it works. What exactly is force? If you remember, we studied force is the rate of change of linear momentum. This is force.
Yes, sir.
External force has potential to change your momentum and state of motion also. If you are running with a velocity of 5 meter per second, I come and push you, and your velocity becomes 10 meter per second, and it takes 2 seconds to do so. Your mass is 5 kgs. Your first momentum P1 is equal to 25 kilograms meter per second. Your second momentum is 5 kgs multiplied by 10 is equal to 50 kilograms meter per second. Your change of momentum is 50 minus 25 is equal to 25 kilograms meter
सर
per
आपको वैसे
second.
दिख नहीं रहा है जो आप लिख रहे हो.
Come again?
सर आपको दिख नहीं रहा है जो आप लिख रहे हो.
You have to be on the page 2, Niche. I'm on the page 2.
H2.
Go on the right hand side, you will see 100%, then the mini map, and then the page 1, 2, 3, 4 on the right hand corner below.
Okay.
So go to page number 2. Yeah, you're there. I can see you. So I have written the momentum of this mass, the initial momentum, to be 5 kilograms into 5, okay? 25 kilograms meter per second. Then after 2 seconds, the momentum comes out to be 50 kilogram meter per second, which means there is a change in momentum of this quantity. Right? Momentum is written as, how is the momentum written? P is equal to M into V. This is the amount of motion in a body. This is your linear momentum. The rate of change of linear momentum will give you the force. This is the second law. But if there is, so in this situation, the body has undergone a change of momentum, which is this much. So there is a change of momentum, okay? So there is a change in momentum. There is a change in momentum, right? So change in momentum is there, which means it took 2 seconds. So the force can be calculated. So you can say that change of momentum divided by the 2 seconds, 25 by 2 is equal to 12.5 newtons. Okay.
Great, sir.
Right. But what if dp comes out to be 0? There is no change in the momentum, which means the force will be equal to 0. This is the law. If there is no external force on a system, then the linear motion, the amount of momentum it has, remains conserved. It only exchanges between the bodies. But there is no external force, which happens in the case of collisions.
अगर रेट ऑफ चेंज ऑफ मोमेंटम अगर लाइक 0 है, तो सर हम ये बोल सकते हैं कि वेलोसिटी कांस्टेंट है.
कह सकते हैं, फॉर अ सिंगल मास कह सकते हैं, assuming the mass remains the same, right? Mass
acceleration 0 आ जाएगी ना.
Acceleration 0 आ गई. The law of conservation of momentum is actually trying to tell you that only force has capability to change momentum. Otherwise, whatever changes you may observe in the absence of an external force may be just exchange of momentum between the bodies. How so? There is a body with m1 v1, and there is another body which is m2 v2. The initial momentum of both is known. Now this body is moving and it collides with this body. After the collision, this is the way it looks like. The first mass now has the velocity v3 and the second mass has a velocity v4, right? The impression you will carry in your mind is, so the velocity of v1 has become v3 after they have collided, and the velocity v2 of the second mass has become v4, right? And therefore, individually, if you notice, each of the body has undergone a change of momentum. This body also has undergone a change of momentum because the velocity has changed. But remember, whatever is the change in momentum of the body 1, if you calculate it to be delta p1, and if you calculate the second body and try to calculate its change in momentum, which is very simply m2 v4 minus m2 v2, and for the first one also you can write it as the final momentum minus the initial momentum. What you will find here is that m2, this delta p, which is the momentum change of the second body after the collision, versus the momentum change of the first body, the sum of these two momentums will still remain to be zeros, which means if one shows a momentum change of x kilogram meter per second, the other will show minus x kilogram meter per second, because in this collision that happened at some point when they touched each other, and there was some exchange of motion between them by virtue of the collision, there is absolutely no involvement of an external force which has added any extra motion. It is just getting exchanged between the two and appears as numbers. If this number earlier was 10 and this is 4, the total system had a momentum of 14. And now, if you notice after the collision, and this comes out to be 6, then this will be 8, because the sum has to remain 14. There was no external force that came and hit either of them. If they collided with each other, momentarily there was a action and reaction pair, but an action and a reaction pair at the time of collision is an internal force which both face and therefore undergo a change in velocity. But the internal force of action and reaction is not like an external force. Nobody has come and pushed it, given it an extra push. They were moving, they collided, and then after the collision, they continued with the linear motions in the straight line. The product of m1 v3 plus m2 v4 has to be equal to m1 v1 plus m2 v2. Absolutely no change, because the system has no source of external force. So if you notice, if you have this situation on a billiards table, which is a simple situation which you can note, two balls are there. This ball has 5 kilogram per meter second. You take a shot at it. This is your white ball. That's your red ball or green ball. Both are, for example, 100 grams and 100 grams. This ball comes with a velocity of 5 meter per second, hits it, both are identical. No, the white ball becomes stationary and the green ball starts moving. Since they're identical and the momentum has to remain conserved, what should be the velocity of your green ball now? There's an exchange of momentum between them. Earlier, this had a momentum. It provided the momentum to this ball, and the green ball started moving, and the ball which provided the momentum becomes stationary. So if this momentum was, 100 grams divided by 1000 m into 5 meter per second, which is 5 by 10 is equal to half kilograms meter per second. What is going to be the momentum of this ball now? White has provided complete momentum transfer to the second body. So this also will have a momentum of they collided at certain point. Okay, it came, it hit it, and after that you observe them. White came to stand still, just like green was, and then the green ball started moving. There was an exchange of motion between them. The quantity of motion contained in white got delivered to green, and green started moving, and white ball lost its motion and became stationary. Any doubts in your mind that come that there is no involvement of external force at all? Momentum has to remain conserved.
हम stick use नहीं कर रहे हैं.
Which stick?
वो billets वाली.
हाँ. That is the one that initiated the velocity of 5 meter per second. जब आपने मारा था, उसको आपने 5 meter per second की constant velocity दे दी थी. Or you can say it was already in motion and then it collided. Forget the providing of force or anything like that. It is not accelerating. It is with 5 meter per second constant speed. So it doesn't change its velocity through this motion. It remains 5 meter per second. Make sense to you so far? All right.
Yes.
Okay. Now, similarly, you have a situation in which there is an XY plane. This is one mass. It is moving in a particular direction. There is another ball which is moving in another direction. This is moving with 50 meter per second and has a mass m1. This is a mass of m1 by 2, is moving in 25 meter per second at an angle of maybe I plus j, right? This is the direction of the velocity, 25 meter per second with I plus j, and this is 50, and this is maybe I plus 3j vector, something like that. So 50 multiply, so this will become 50I.
m.
Huh. The mass is m1 by 2. This is the magnitude, some magnitude. So the velocity vector of the second.
तो ले रखा 50m और 25m ही ले लेते हैं.
So I'm taking that. So 25 I meter per second था वो. Forget it. Okay. So I will remove this. 25 I plus 25 j is the velocity vector of the second one, which is a mass of m1 by 2. The velocity vector of the first one is 50 I plus 150 j, and it has a mass of m1. They undergo a collision. After the collision, you notice that the velocity of the second mass has become 100 I plus 50 j. Mass is still the same, obviously. My question to you is, what is the new momentum of the first ball, which is m1, after the collision? So this is the situation after the collision. The second ball after the collision has acquired a new velocity after, so I'm writing f subscript. This is initial. Now if you try and calculate this, your total initial momentum is m1 into, because its momentum is a vector, and therefore I'm writing it vectorially, 150 j plus the initial momentum m1 by 2, 25 I plus 25 j is equal to, so this is your total initial momentum. In the final momentum scenario, you have to find the velocity of the first mass m1. So the final momentum scenario, so this is completely pi being written, and I'm writing p final after the collision, m12 into, sorry, at second mass, yes, 100 I plus 50 j plus the first mass, and I don't know what is the velocity going to look like, but I am writing it like this. I will open all the brackets, collect all the i's, which is on left hand side 75 I, and on the right hand side it is going to be 50 I. So this will become 25 I net on the left hand side. If I notice the other one, this is 150 j and another 12.5 j, 162.5. minus 25j. So 162 minus 25 coming from the right hand side will give me 137.5. Okay, approximately. So plus 137j is equal to m1 into, and of course there is a element of m by 2 here also, right? So I'm going to write it as m1 by 2, and this is m1, and this is the only thing which is left with me now, which is m1 into xi plus yj. M will get cancelled, so I'll be left with 25i plus, so this will become half 60, roughly around 68.5. Let's say 68j is equal to xi plus yj. So now you know that the first ball acquired a velocity of 25 meter per second in x-axis and a velocity of 68 in y-axis, and therefore is having an angle of alpha which is 68 upon 25 as a direction of its motion. Maybe it looks like this. So you also have realized that you can do vectors on this. So if P initial of first and the P initial of second are added, they are equal to P final first plus P final 2. Any doubts in your mind? We discussed the conservation of momentum in a plane instead of a linear motion. That was the only difference. And we also used our knowledge of vectors to find out the new velocity. There was no external force involved in this. This is the linear conservation of momentum concept.
ये scenario को दोबारा समझा दो.
Okay, so you have one ball with this velocity. I have written its momentum here. It collides with a second ball here, whose momentum is again mentioned here. Its initial velocity is known. Its mass is m1 by 2. So on the left hand side, what you see as this is the momentum of the first mass, initial, and I'm writing 1, initial momentum of first mass. This is the initial momentum of the second mass. Any doubt in this? The total momentum of the system is the sum of the individual momentums.
No, sir.
They collide now. After the collision, it is found that the velocity of the second mass is this much. The velocity of V2 is this much, and its mass is unchanged, obviously. So what I've done is I have written its momentum, final momentum of the second mass.
Okay.
Because I know its velocity. My question to you was, what is the velocity of the first mass, which is this?
ये इसके इक्वल है?
किसके? No, ये तो initial velocity है. This is the initial velocity, which is
पूरा expression sir, पूरा expression.
the sum, yes. Because we're up the sum, right? We are writing this, that the initial momentum of the first mass plus the initial momentum of the second mass is equal to the final momentum of the first mass plus the final momentum of the second mass. This equation represents the law of conservation of energy.
Momentum, linear momentum.
Correct.
Okay.
So you have a sense ki there is no external force, and immediately the your instinct. Sorry.
समझ आ गया.
Okay. All right. Let's do one question then, and see if we can apply this to a real life numerical on momentum, because you can expect derivation also from this, and you can also expect a question from this. Derivation also we will do of conservation of linear momentum, which I have just shown you. dp by dt is equal to 0, but there is another derivation which we will do. Okay, so let's say we pick up a question and try and solve this. Okay, so all right. So in some questions you will see this word, okay, and this is an excellent way to understand this. So there is a bomb which is lying here, okay, like on a Diwali day, you use a little bomb. Okay, it it explodes. It explodes. A piece of it, which is small piece of it, which is around 25%. So 1/4 of it moves towards the right side with a velocity of 5 meter per second. The question to you is: so this is a bomb. It explodes,
और दूसरा कोई और पार्टिकल गिरा
and this is 1/4 the mass of the total bomb. Question to you is: what happens to the balance 3/4 of the mass? इसके साथ क्या? What is its velocity? Mass remains conserved, right? You cannot create mass, you can't destroy. So if you know one part is there, the second part is also there. The question is, what happened to it? The word used is explosion. You have to find the velocity of the second mass after the explosion completed.
second mass
The language is cryptic for sure, right? It's not a straightforward type of language. It is definitely a bit cryptic because it uses the word.
कोई एक्सप्लोजन के साथ करना क्या है
हाँ, exactly. That's the point. Explosion के साथ करना क्या है?
कि पार्टिकल्स दे रखा है जो
Right. Which are the broken parts of it, right? So 1/4 of the bomb goes like this. What happens to the?
यूनिफॉर्म होते हैं सारे पार्ट्स
I think 1/4. If one part is 1/4, the other will be 3/4, right? Law of conservation of mass. So if you're saying uniform means
नहीं मतलब लाइक काफी सारे पार्टिकल्स गिरे या फिर सिर्फ एक दो ही गिरे
two, that's all. Two.
अच्छा
Bomb was lying stationary on the ground and it exploded, and you saw one part going, and you have to speculate, not speculate, actually calculate what happens to the second part, which is 3/4 m.
तो बेसिकली हमें मोमेंटम निकालना है बॉम्ब का
Right.
तो लाइक
Not tough.
बट हमें इसकी वेलोसिटी भी नहीं पता है बॉम्ब की
It is stationary. I told you it's lying there.
इट्स एट रेस्ट
It's at rest. Of course, it is at rest.
अगर ये रेस्ट पे तो लाइक इसका वो नहीं होना चाहिए मोमेंटम जीरो नहीं होना चाहिए
होना चाहिए.
शुड बी आई गेस जीरो
Okay. Write it. The initial momentum of the system, and then it exploded.
पार्टिकल है सर इसको मैं सी मान रहा हूँ इस पार्टिकल को।
No worries. Go ahead. Okay. किसी ने आके उसको या ट्रिगर दबाया और बॉम्ब एक्सप्लोडेड,
बट
राइट?
इनिशियल मोमेंटम लाइक तो एक्सप्लोजन से पहले हो गया ना,
राइट.
तो पार्टिकल भी तो एग्जिस्ट नहीं करेगा पहले।
Which particle? Bomb was already there of mass m.
नहीं, बॉम्ब तो एग्जिस्ट करेगा बट जो पार्टिकल जो निकला बॉम्ब से,
वो तो नहीं था. It was not there.
हाँ जी, तो एग्जिस्ट 0
Correct.
equals to PBF
Very good.
554 M
Okay.
M मीटर पर सेकंड। तो so basically
Correct है. ठीक है.
basically this is the final momentum of bomb.
Yes. Of the bomb. Of the second particle, you mean?
Yes, bomb मतलब पार्ट सेकंड पार्टिकल जो बॉम्ब से निकल के आया।
हाँ. But question is what is its velocity?
Okay. So velocity कैसे निकालेंगे?
All right. So let me tell you. Okay. So your thought process, I'll just tell you what actually happens. Okay. So velocity is not difficult. You can write the balance weight as 3 by 4 m multiply with the velocity, right? And 4 will get cancelled and you will get a velocity of minus 5 by 3 meter per second. So the balance weight, which is a bigger part of it, the 3/4 m goes in the reverse direction with a velocity of 5 by 3 meter per second. The one which is m by 4, the velocity was already given as 5, right?
5 by 3 नहीं 5 by 4.
5 by 4. Okay, let's call it 5 by 4.
Yes. Okay, समझ आ गया.
But I'm not checking your calculation right now. I'm just telling you so your momentum of this mass was known to you. So you wrote it as 5 by 4 m. And then you said the sum of the momentum, which is 3 by 4 m into its velocity, should also stay 0. Because initially it was 0, right?
Yes.
And so you found out velocity is equal to minus 5 by 3 meter per second. Okay. Don't worry about calculation right now. We're concentrating on something else. Let me tell you the way to think about it is obviously the two have moved in opposite direction. This is clear from the answer. Because momentum cannot get generated all of a sudden. Most of the students have this confusion. So this is a bomb. It explodes. And the students have a question that due to the explosion, there is an external force on the bomb. And then the momentum gets generated. We know already what happened. But the confusion is whatever you wrote as a momentum, after the collision also, which means when the bomb explodes there, the force generated by collision is exactly identical to the action and reaction pair when the two masses collide on the surface. They exchange motion with each other, the quanta motion, which means they exchange momentum between them, but the sum always remains the same. So even though they're colliding here and they have a force between them, which is action and reaction, like this, they're colliding with each other, but it is not to be taken into account as an external force. And similarly, when the bomb explodes with a force, the force of the collision, which is internal, which is more of chemicals burning, and the burning producing a thrust or a. Can you allow me to complete, please? Let me complete, and then you can say anything you want to. I'll give you the opportunity. So this is your. This is a case of internal forces, and therefore the force which got generated by the chemical burning or the pressure or whatever you want to call it is not to be taken into account. And hence your equation was correct, absolutely right. But what you should have thought extra was at the time of explosion, whatever forces are getting generated are internal to the bomb. They are not an external force on the bomb coming and getting applied. Your opportunity. Go ahead, please.
तो ये ऐड करनी थी
क्या?
Force.
No, I said it is an internal force, just like this. This was not when the two bodies collide and the momentum remains conserved. There is an action and a reaction pair here also, right? At the time of collision. But these are not to be treated as external forces. These are internal to the system. And similarly, the explosion force is also internal force. Nobody came and pushed the bomb with a force of 5 newtons, right? Nobody. Just the internal chemical of the bomb produced a force internal to the bomb. So therefore, it is not to be treated as external force. It is to be treated as an internal force. That's the point I'm trying to make. Even in a collision where the exchange of momentum happens between the two bodies, these two bodies are moving, say they're moving in the opposite direction, they collide. Now this is the scenario of collision, and they touch each other. And when they're touching each other, if you draw a free body diagram, the right one is applying a force here, and the left one is applying a force here. But are we considering this to calculate momentum? No. This collision also, just like an explosion, is internal to the system, between the particles of the system. No one has come externally at the point of collision or otherwise to say, okay, I'm applying 5 Newton extra force now. Then you can say some extra motion has been added to the system. But if it is an internal collision, like these two bodies coming towards each other, it does not add anything to the moment, the quantity of motion. It doesn't add anything. Doubts, feel free to ask.
Yes.
So even in a law of conservation of momentum, somebody can say collisions are happening, but the forces of action and reaction are always internal to the system. They are not external. They exist in a pair. Similarly, in a bomb explosion also, the forces which got generated that resulted in the separation of this whole thing was internal to the system. It did not come from outside. And that is a confusion most of the students have, that when it exploded, there was an internal force that was there that resulted in all of this. No, it was internal, and therefore, if you know the momentum of one, you can add the momentum of the second particle and still keep it zero, because that force in your mind is internal, not external. Right?
Yes, sir.
So I will not introduce any ideas in your mind at the moment. I think what we started was with the concept of
inclined plane,
right? And we did some few tricky problems, lot to come when the friction also gets introduced. So you have a grip on the inclined plane. You do understand that a new coordinate system got created, and then you also understand, once you are comfortable with that new coordinate system, on that coordinate system you can apply the second law of motion with the same ease you were applying on a horizontal surface. The only thing that has happened now is some resolution which has happened, but in reality nothing has changed. It's a way of looking at it. What appears to be a twisted form of xy coordinate and different way of doing it is actually one and the same thing. Only thing is, in that frame of reference or in that coordinate system, people will observe things in a different manner, and they will say, okay, because I'm standing like this, I don't know, there is a horizontal there, I will say I am horizontal, I look at, but you are standing away from the system on the ground, you will say you are inclined. The guy on the incline doesn't know he's inclined. For him, that's his new coordinate system. But you know that it's a translation, which means the x-axis has moved by a theta angle, and so everything will now be as per the new coordinate system. This is called translation, or conversion of one system into another, and then solving Newton's second law of equation. That's the first thing you saw. And then you started doing numericals on inclined plane, and gradually you got also a very big hint that friction has to do with tendency. It appears in response to tendency. It does not start on its own. First, it will see the tendency due to the external force, then it will come into play. This is another important observation you did. Then what you did was you also clubbed the idea of tension and a inclined plane together. You assumed that heavier weight should take it down, but it did, because you did not realize there is a concept of angle of a ramp that may change the values in a way that instead of going downward, although it looks heavier, but the angle makes an impact, and the net resulted is that the bodies are moving upwards or downwards like this, right? And you applied the tension very correctly. You actually understood it, that the tension has to be applied in a particular manner, which is a pull. But in the second part of the question, where you were solving, I think what you did a slight amount of error, which is how do you apply the force on this mass, right? Which is where you faltered a bit, slightly, but you corrected yourself immediately because you realized these are connected system moving in the same direction. Therefore, this mass should also go down if this is going upward, right? So be careful of that. And then, of course, after doing some work on this, I took you to the law of conservation of momentum, and in the law of conservation of momentum, you realize that a second law is actually nothing but a rate of change of momentum, and that rate of change of momentum when becomes zero, which means there is no external force, because the rate of change of momentum is force. If you're putting it as zero, then there is dp, the delta p has to be zero, and that delta p told you that the final momentum minus initial momentum is equal to zero, and therefore the final momentum is equal to the initial momentum. Only exchange of motion happens, the quanta of motion, which means some velocities change here and there as numbers, but nothing else happens. And then you took it to the next level of solving it on the basis of a coordinate system of ijk to see the vector nature of the momentum, right? You found the velocity just by doing left side addition and right side addition and finding the value of xi plus vj. And then what you did was you solved a question in which you realize that it is an explosion, but it is internal nature. It is very similar to two blocks striking each other. When they collide, they have action and reaction between them, but it is not to be taken as an external force. So the moot point or the broad point or the meat of the matter is, when you're doing the questions of linear momentum, be very careful when you're solving. Is there an element of external force or not? If not, conserve the momentum and apply the momentum equations on the respective mass before the event of collision. The event could be firing of a bullet. the bullet goes out with a momentum mv, and the gun faces a recoil momentum of the same quantity, but because the gun is very heavy, a single bullet really doesn't make too much difference. But if you have weak shoulder, the momentum which comes back to you in the negative form, because it has to show that the overall momentum of the bullet plus the gun has to remain conserved. The net is zero because the forward momentum and the backward momentum, the sum is zero. Because the gun is very heavy, therefore the velocity is very small. You don't really observe it, but some people do observe it. Depends how fast the bullet went out. So I'm sure you have understood to an extent what is the law of conservation of momentum. We will do now a lot of use cases of momentum where we will study. One of the examples you also took was on the billiards ball, where you said they will stick with each other. When I said no, it may stop and it may transfer its momentum to the second body. So we will study all those scenarios, like a car crashing into a big truck, the two balls sticking with each other, the two balls striking and going away from each other. And then we will also understand another terminology called as coefficient of restitution. Whenever a collision happens, it defines how the collision looks like. And all those conditions which we discussed, which is whether they will stick together, whether they will, the momentum will get replaced if the masses are equal, so on and so, or maybe the bodies collide in a manner that they go at an angle with each other, right? They don't collide linearly, like center to center collision. It's called an oblique collision. So two balls normally when they collide, their centers are colliding. But sometimes they may collide like this, which means the centering is not correct, which means when they collide, this may go like this as an oblique and may also transfer some of momentum in this direction for this ball. So this ball may go like this because the centering is not there. An angle gets introduced. So we will study coefficient of restitution. We will study oblique momentum. Oblique momentum is a bit advanced in nature, but for joint entrance examination, it is very, very important to understand the concept of oblique momentum. So momentum in itself is a lot to cover, but coefficient of restitution is more important for your upcoming examination. Make sense to you, the sequence we are going with?
Yes, sir.
Okay, so please go ahead and take time out, try questions from your assignment now. Feel free to ask me your difficulties, what you're facing in your assignment. You will be able to do some of them. If you still face a problem, we will open up your assignment and do it. And in the meanwhile, tomorrow we will continue to do this discussion of momentum, which is especially the discussion around coefficient of restitution. It's a new idea that will come into your mind. It's a fantastic idea to understand the different scenarios of sticking together, a car crashing into the big bus, stopping, what happens, and so on and so forth. Practical importance in everyday life also. Okay?
Yes, sir.
Anji.
End the live stream.
All right. Will do. As soon as we close, it will get closed.
करना भी live stream end कर देना.
ठीक है. I will do that. All right. See you tomorrow then. Thank you.